Okay, welcome to note set number 4, where we'll start talking about the geometry of vectors. In the last set, we talked about the arithmetic aspects. We talked about how to add them together and subtract them, how to multiply by a scalar, and we talked about this really big idea called linear combination. And if we did a linear combination of vectors, we could make a new vector. Just by changing the weights that we put on each of them, we could make a variety of different vectors, so that's a big idea. And we did start to look a little bit at the geometry of the vectors. So we could plot them so that we could visualize them on a set of axes. And then we talked about visualizing where the linear combination will lie. And this idea, being able to look at a set of vectors and think about what can I build from them? What are all the different possible vectors that I could build from them? Huge idea here. So focus on making sure you can think about that. So again, as I said at in one of the first lectures, this course is not about a canned set of rote steps that you just regurgitate. It's about being able to think and visualize and understand. So we're going to dig deeper into this idea of the geometry of vectors and think about, we could visualize and think about, okay, this vector is longer than that one because on the plot it extends over a greater distance. But how do we measure that if without drawing it, just given the numbers, or even just arbitrary specification of the elements? How do we determine what the length of that vector is going to be? And we introduce a new name, a new term called the norm. So the norm of a vector is nothing more than the length of the vector. So we just need a special name because the mathematicians say that's what we need to call it. And well, in 2 dimensions, we can think about the angle between 2 vectors. We can visualize that. And even in 3 dimensions, you could visualize the angle between 2 vectors. But what if I gave you 2 vectors that each had 1,000 elements? So we're in R1000. What's the angle between those 2 vectors? Can we even think about that idea? Well, we can, and that'll lead us to something called an inner product or a dot product. So the textbook likes to use the word dot product. I prefer the term inner product. That's just what I picked up when I was learning this stuff. So I'll say mostly stick with the term inner product. I think it's a little more descriptive and general use than dot product. Different people use both of those. And we're going to kick all this off with the idea of independence of vectors. So if we go back to the challenge questions that we had towards the end of the note set number 3, we asked 3 questions. So you've got some vector u, and we wanted to know if I varied the coefficient c in front of it, could set it to anything and everything, what do I get? And what we said was that we get a line that goes through the origin. And so we hit the origin when the variable c is set to 0. And by setting c to various positive and negative values, we can make u stretch out in both directions along some line that goes through the origin. Then we said, suppose I've got a u and a v, and I combine those, linear combination, weighted with some numbers c and d. And we said that, well, we visualized u and v as 2 pencils, and we said if you put the erasers at the origin, and then you lay a stiff piece of cardboard so that it touches the pencils, lies flat on the pencils, that plane will be the plane that is determined by this linear combination. Now, you're probably visualizing this in 3 dimensions, But that same idea extends to higher dimensions, even though you can't see them and visualize them. 4, 5, 6, or 1,000. So if I had two 1,000-dimensional vectors and I wanted to form a linear combination from them, there would be some two-dimensional surface in that 1,000-dimensional space. So, think about it in terms of a two-dimensional plane in a three-dimensional space, and then just let your mind wander up to 1,000-dimensional space. I know it's a little hard to think about, but after a while you get able to kind of twist your mind around that. You can never really see it, but you just kind of ignore the fact that you can't see it and you can kind of feel it. Well, what if we have three vectors that we combine together? And we said, well, that would give us a three-dimensional space. So just like a plane in 3 dimensions is a two-dimensional surface in 3 dimensions, we could have a three-dimensional surface in 1,000 dimensions. So I know it's hard to visualize, but the math works. And we said that there was a caveat to all of this, with the exception of the first one. So this one there's no caveat on. Well, other than u cannot be the 0 vector. But for these two, assuming u and v, neither one is the 0 vector, and furthermore, that in this case, u and v don't lie on the same line, and in this case, u, v, and w don't lie in the same plane, then these things are true. And so this caveat, this requirement that makes us able to ensure that we can kind of get the biggest amount of diversity out of 2 vectors, or the biggest amount of diversity out of a linear combination of 3 vectors, that's what we're going to look at now. How do we capture this idea of 2 vectors not on the same line, or 3 vectors not in the same plane? And that leads us to the idea of independence of vectors. And some books will refer to this as specifically as linear independence. But when you're in the middle of a linear algebra course, linear independence is kind of redundant. Independence says enough. So let's sneak up on this idea and talk about this example where we've got 2 vectors that we're forming a linear combination from them. And we say that it's a plane that includes the original vectors, that goes through the origin. So there's 2 vectors, u and v, and so they are in a 2-dimensional space, and so the plane that they form is the entire plane that constitutes this 2-dimensional R2 space. So it's true in that case. Now we could pop one of those out of the plane of the screen, and now our plane would cut through the plane of the screen, but we would still have a plane that they go through, as long as neither of them, as long as they don't lie on the same line. So in that case, we cannot create vectors in a plane, right? So if we take c times u, all we're going to be doing is either stretching this down this way, or flipping it around and stretching it along this way, or scrunching it. And so when we add that to v, we're going to end up back on this line. So the only thing we can create are things on that line. So certainly if u and v lie on the same line, we cannot use them to create a plane. So the linear combinations would not, the set of all possible linear combinations would not form a plane in this case. So that's the caveat for the 2-vector case. So that leads us to defining this idea of linear independence. So we say that 2 vectors are independent if there is no line on which they both lie. So that is the case over here. There's no line on which they both lie. And by that we mean a line through the origin. So there's a line that v lies on. Here's the line that u lies on, and they are different. But here we see that line right there, the blue dashed line, both u and v lie on it. So this case, the vectors are linearly dependent. And for this first case, the vectors are linearly independent. And now we'll just generalize this idea. So now we go to the third question. I've got three vectors. I form a linear combination of them, and I want to know, if I look at all possible linear combinations, what kind of thing do I form? What kind of structure? And we said, well, it's a three-dimensional space, R3. So here's an example where that's true. So I've got both u and v lie in, so I've got some axes here. I've got axis 1, axis 2, and axis 3. So those are corresponding to the element position. So u has a value of 1 on the first axis and negative 1 on the second axis. So that's why it points out here. V has 1 on the first axis and 1 on the second axis. And the vectors don't quite look like they have the same same size, but that's just because of the characteristics of the drawing. And then W has 0 elements along the first two dimensions, the first two axes, and just has a component of 1. So it sticks straight up out of the plane formed by the 1 axis and the 2 axis. So in that case, this is true. If I tried to combine these things using a linear combination, this is what I could form any vector out of these three vectors, and you should try to visualize how you might do that. But if W lies in the plane of u and v, so instead of W sticking up straight out of the plane formed by axis 1 and 2, if W also lay down here in the same plane, notice that the plane defined by axis 1 and 2 is the same as the plane defined by u and v. So if W were to also lie in that plane, then I'd only be able to create things in that plane. I have no component that sticks out of the plane, and so anything that lies out of that plane is unbuildable. So for this case, I would not be able to build R3, but for the first case, I can build all of R3 through linear combinations. So now we say that three vectors are independent if there is no plane on which they all lie. Okay, so that's pretty easy, straightforward. So we say two vectors are independent if there's no line on which they both lie. Another way to say that, just going back and revisiting this, we can say that u and v are not independent if u is equal to some constant times v. So this is just another way of saying this, right? Because if u and v lie on the same line, by multiplying v by c, I can, stretch v or shrink its length to match u, or if u is pointing in the opposite direction, I can flip it around. So if we go back to this example here, let me clear this off here. So this is the case that we're talking about. I can multiply v by some number c. In this case, it would have to be negative and a little bit less than 1 to make the result match up with u. So that's the scenario that we're looking at here. So we say that an alternate way of expressing this idea of linear independence is that two vectors are linearly dependent if I can write one as a scalar multiple of the other. And I could do it for the other way around. I could say v is equal to some constant times u. It doesn't really matter. In this case, that constant would be 1 over c. Notice that it has to be a non-zero scalar. So that instantly makes sure that u and v, neither of them is the zero vector itself. So when we say not independent, another way simpler to say that is to just say dependent. So similar to that, we can say that three vectors are independent if there is no plane on which they all lie. Or an equivalent way to say that is that three vectors w, u, and v are not independent. We can just cross all that out and say are dependent if I can write one of them, in this case I'll just pick w, as a linear combination of the other two, as long as c and d are non-zero. So then, if I can write it that way, then they are dependent. And we could write this a different way. I'm now going to drive to a different way of writing the same idea, which is a little better way to write it. So let's put a negative b in front of w. We're going to keep the c and the d there, but listen carefully. The c and d that I have here are going to have to be different c and d than I have up there. Okay, but I think you can see that these two things are equivalent to each other. I really could put like a c hat and a d hat here if that bothered you. And let's actually do it the other way around. Let me get rid of that, and let's put a c hat here and a d hat, and then leave the c and the d down here. So the numbers will be different. So once I've got that set up, which is really just saying the same thing as this, then I can swing the b over to the other side. The negative bw, I swing it over to the other side. I add it to both sides of the equation. And now I get a linear combination of the three of them. So we say that three vectors are dependent if I can pick three non-zero numbers for a linear combination of them that will add up to zero. So that's equivalent to saying that I can write any one of them in terms of the other two. And the advantage of doing it this way is that I don't have to commit to saying this is the one I'm going to write in terms of the other two. And it also nicely generalizes to any number of vectors. So vectors u and v, now we're going to put a slight different twist on this. Our three vectors w, u, and v are independent only if adding them, doing a linear combination of them such that it is equal to zero requires all three coefficients to be equal to zero. So if the only way I can linear combine them to give zero is to have all three weights be zero, then they are independent. So this is a very strong condition, and we'll use that over and over and over. So make sure you think carefully about that and burn it into your brain, not as a memorization. I do not encourage people to just blindly memorize things. What you should strive for is to capture the reason why that's true. Work your way through this development here so that that idea is stuck into your head, not because you've rotely memorized it, but because the idea makes sense to you. So now we can generalize this to even higher dimensions and other numbers of vectors. Well, to be fair, we didn't say anything about dimension when we talked about those three vectors. You were probably thinking 3 dimensions, but we didn't say 3 dimensions. We just said 3 vectors, any 3 vectors. So we could have been in a space of dimension 1,000 or 2,000 or 1,000,000. But now we can say 4 vectors are independent if there is no 3D space in which they all lie. So there's no way we can pick 4 vectors in R3 that will be linearly independent. We could pick 3 vectors in 3D space. Those all could be chosen to be independent. But as soon as we try to pick a 4th one, and have it still be in R3. There's nowhere to put it so that it will be independent from the others. 5 vectors are independent if there's no 4D space in which they all lie. Wow, 4D, how are we visualizing this? Well, like I said, you can't. You can't visualize this like you can 2D or 3D or 1D for that matter. But you can kind of catch the essence of it. So you've got this 4-dimensional space. You've got 5 vectors in there. Yeah, it's a little bit hard. So even though we can't visualize this, and that's what makes these views or these ways of expressing independence a little hard to deal with, we can always rely on a more mathematical way to do it. So one way we do it is to say a set of vectors, v1 through vm, didn't say anything about the dimension of the space, so they could be in any dimension space we want. So that set of vectors is said to be linearly independent if none of the vectors in it can be written as a linear combination of the others. So v1 can't be written in terms of v2 through vm. v2 can't be written in terms of v1, v3, etc. out to vm, and so on. So each one of them by themselves can't be written in terms of the other. So that's one way to write that, or to think about that. And all I've done is just rewritten that up at the top because we're going to now extend this view. So that's nice. Allows us to think about it, but it's kind of hard to check. You have to sit down and say, okay, can I make V1 from V2 through VM? Can I make V2 from the others? Can I make V3 from the others? So it's kind of a pain. But now, this is completely equivalent, and we led up to this when we talked about the 3-vector case. We had an equivalent to this, and we showed that by using that negative b thing that we could get to this point. So now we say we've got v1 through vn. I switched on you. I said n here and m there. No big deal. N, m, they're integers, arbitrary, so it doesn't matter. So I've got some set of vectors, v1 through vn. They're independent if the only way I can make the linear combination be equal to 0 is by setting all the coefficients in their weight to 0. Now that's the real firm way to define linear independence, and that's the thing that we're going to be referring back to. So between the two of these, this one, we can't write any one of them in terms of the others. That's one good way to think about it, but the strongest, best way is the only way I can make the linear combination go to 0 is by setting all the weights to 0. And this is something that we'll be able to check fairly easy. Not now, but as we go through the course. Okay, so we've got this idea of linear independence established, and we're going to put that aside for a bit. The idea of length of a vector has nothing to do with linear independence. And so, we've already visualized in 2 space and 3 space the idea of the length of a vector. Well, you draw the point where it's supposed to be on the set of axes, and how long that, or how far that point is from the origin is the length. But how do we characterize that mathematically? Oh, and we also said that another term for length is norm. So we will sometimes use the term length, but we will often use the term norm. So you ought to just get used to using that. And how we denote, that was a combination of denote and norm. How we denote the norm of a vector is usually with these double bars on each side. But sometimes we write it out, norm of v, but I prefer this. It's a little easier to write out. So here's a vector in 2-dimensional space in R2. First element is 3, second element is 2, and we can see how long it is. But we also can see by the Pythagorean theorem how we should characterize its length, right? We've got 2 on this side, So we've got a 3 and a 2. So this is a 2, 3. So we would square 2 to get 4, square 3 to get 9. So we've got square root of 13, right? Did I do my arithmetic right? Yes, I did it correct. I have forgotten that I put that there. So the length of this vector from the tail out to the tip has units of square root of 13. You know, the same units as whatever these are. So if these are in units of meters, then this will be square root of 13 meters. If we're talking about a force vector, those might be in units of newtons. If we're talking about a velocity vector, they could be in units of meters per second. So whatever. So that's the idea. And a simple formula that we can easily see in 2 dimensions comes from Pythagorean theorem, so it makes complete sense, and leads to a more general view. So if we've got n dimensions, we square every single element, add them all up, and take the square root. So we just saw how to do that in 2 dimensions. We took the square plus the square. That's the adding, squaring and adding up, and then we took the square root. Now, sometimes we're more interested in working with the norm squared for a variety of reasons. Hopefully that'll become clear as we go through this. And so if we square both sides of this, we square this, it'll get rid of the square root, and we're left with this. So the sum of the squares of the elements is the square of the length, which we call the norm squared. And so we put a little square sign up there. So some properties of the vector norm. Remember, this is just talking about the length of a vector. So if I multiply a vector by alpha, we've already seen that alpha can flip-flop that vector, but it can also stretch it or scrunch it in length. And so here is the mechanism by which it stretches and scrunches. So the absolute value is necessary because the length of a vector cannot be negative, right? We got a bunch of squares going on up here. So we're adding up a bunch of positive numbers and taking the square root, and technically we should say taking the positive square root. Okay, so the norm can never be negative. Could be 0 if all the elements are 0, obviously. So that's why we need the absolute value on the scalar, because the scalar itself could be negative, which is flipping the direction of v, but not necessarily changing. The flipping doesn't change its length. And then we've got the idea of a generalized triangle inequality, and this is a workhorse result, more so in a course that's oriented towards proofs of theorems. This one gets applied a lot in proofs, but it's also handy when doing more engineering-oriented type computations. So if I form a linear combination between 2 vectors, v1 and v2, what's the resulting vector's length relative to the individual vector lengths? And we see that it's less than or equal to the absolute value of alpha times the length of v1 plus the absolute value of beta times the length of v2. And we can see that over here. Here's a nice picture of that. I show v1, I show v2. I do the little moving v1 over to here, tip to tail, or tail to tip rather. And so this point out here is the tip of the v1 plus v2. And so all this inequality is saying is if I traveled from the origin out to the tip directly along that vector, despite my mouse action being a little shaky there, I would travel less distance than if I went along v2 and I went along the length and the translated v1. So that's what that triangle inequality shows, and it's just a generalization of the triangle inequality that you learned in 2 dimensions in your probably in your geometry class in high school. The other thing, or another thing, is that the norm must be less than infinity. So we can't have a vector that's infinitely long, but we can have vectors that are arbitrarily bigger and bigger and bigger in length. Just like the real numbers don't actually have the number infinity in them, but the numbers go towards infinity. So you give me a real number and I can find one bigger than that. You give me a vector with a certain length and I can find one longer than that. And finally, the last property that we'll list here is the fact that the only vector that has norm equal to 0 is the 0 vector itself. So the only way we can get this thing to add up to 0 is, because of the squares, is to have every term in that sum be 0 itself. Sometimes we will refer to something called a unit vector. And so in mathematics, we use the word unit to convey something about one. So, in economics, you know about the unit price. So the price of one standard quantity. So the unit price for, if you go to buy, soda, you might see a unit price for the standard quantity, which might be ounce. I don't know. So the price per ounce. But in mathematics, we'll talk about the unit cube, which is a cube whose sides are all length 1. We could talk about the unit circle. It's a circle with radius of 1. And for us, we'll talk about a unit vector. It's a vector whose length equals 1. It can point anywhere, and it can be in any number of dimensions, but its length is 1. So there's not just one unit vector. There's infinitely many unit vectors. And you give me a vector v, and I can always create a vector that's a unit vector associated with it by taking v and dividing it by its norm. We can now use the properties of norm to show that if I take the norm of u, I'm going to take, should do double. By the properties of that, I can pull this out front, and I have a 1 over norm v times the norm of v, and so that equals 1. So the cool thing about this, and this comes in handy sometimes, so you give me a vector v, I can create a unit vector that points in the same direction as v by doing this. We say that we are normalizing the vector when we do that. So that'll crop up from time to time. So here's some examples of some unit vectors. These names I and j are kind of famous standard names. If you've taken Calc 3, you've probably encountered the I, j, and k vectors in Calc 3. So that's the only reason that we name those here. So the I and the j have nothing to do with complex or imaginary numbers, where those letters are also sometimes used. So notice that these are kind of the axis vectors, right? So if we have a two-dimensional space with these axes, I lies along this axis and j lies along the vertical axis. In the same two-dimensional xy plane, if we create a vector, call it u, whose first element is just cosine of theta and second element is sine of theta, and we think about rotating this vector around to any angle theta, the tip of this will, I claim, go around a circle of unit radius. So this is a whole set of unit vectors, and in fact that set includes all possible unit vectors in two-dimensional space. Now, using tricks from trig identities, you should be able to prove, given this definition, that that truly does, regardless of the value of theta, really does have unit norm. So I encourage you to do that. Now, from norm, we move into something called dot product or inner product. And I'm an inner product guy. I will call it inner product much more often than I will call it dot product. But some people use dot product, some people use inner product. And so the inner product is something that takes two vectors and gives you back a single number that characterizes something about how those two vectors are related to each other. So this is a really, really, really big idea in this course. I really cannot stress how important this idea of inner product is. Almost everything in the field of signal processing boils down to inner products. Lots of stuff in communication systems. So if you're interested in how information is sent from one place to another over cell phones, believe it or not, the concept of inner product is going on inside your cell phone millions of times a second, believe it or not. So the number that this gives back tells us something very important about these two vectors. It tells us how alike these two vectors are. And by that we kind of mean how aligned are they? In what way are they aligned with each other? Or how do they point in the same direction or not? So we'll define this first for 2D vectors and then extend it into higher dimensions. So suppose we've got a vector v and a vector w, and I'm just pointing out that this is not saying that this is a row vector. This is just a convenient way to write a column vector without having to write it vertically. So notice we're not using the square brackets, and we put a comma between them. So we've got two-dimensional column vectors, and this book likes to use the dot here to represent inner product, and I actually prefer a different symbol that we'll see in just a little bit. So we define the inner product as you multiply the two first elements together, you multiply the two second elements together, and add them up. So if we're looking at this these two vectors, we take these two, multiply them together. We take these two and multiply them together. So you can kind of think about lining the two vectors up, one over the one next to the right next to each other. Think about them as columns, and draw a line vertically. So if we had these as columns, we would have V1 and V2, and then we would have W1 and W2. Sorry about the scratchy writing here. And we would just line those two up and multiply them, and line those two up and multiply them, and then add the results. And that's the inner product. So very easy to compute, even for much higher dimensions. Yeah, there's the symbol that I like. These angle brackets with a comma in between. And that's a very common notation within the fields of communications, signal processing, control systems, and so forth. There's reasons why I like that, aside from the fact that that's how I learned it. So here's an example. Here's our two vectors. And if you calculate their inner product, so you take 4 times -1 gives you -4. Take 2 times 2 gives you +4. So -4 plus 4 gives you 0. So the inner product between these two vectors, these two that are given, is equal to 0. If we were to change those vectors, we could get some other value for their inner product. Now, whenever you see 0 showing up someplace, you ought to at least consider the fact that something special might be going on, because there's some very special, a few special numbers in math. The number 1 is a special number. The number 0 is a special number. And there's a few other ones. E is very special. The imaginary number I is very, very special. And the number pi is very special. And there's actually a famous equation that relates all five of those numbers. E, I, pi, 1, and 0. Yeah, all five of those numbers can be related together in one single equation. When you go through this video, if you know what that equation is, send me an email and let me know. I'd be interested in seeing if you know what it is. Well, don't send me an email if someone else is using these videos to teach a course. Send them the email. And if they haven't watched this video, they'll be wondering why you're sending that email. That could be fun. Anyway, what's so special about these two vectors? Well, let's take a look. If we plot them on a set of axes, and they're in 2 dimensions, so we can draw 2 axes, and we carefully plot them. What do we see about them? Well, we see, hey, this looks kind of like a right angle there. And in fact, that's a key idea. Anytime 2 vectors have an inner product that's equal to 0, then the angle between those vectors is like it's a right angle. Now, in 2 dimensions, it's obvious to visualize that. In 3 dimensions, you can still visualize that. Take your 2 pencils, put them at a right angle, anchor them down on anchor their erasers down on the origin on your table, and kind of swivel them around while keeping the right angle. So you can have 2 vectors in 3-dimensional space be at right angles with each other. But this holds true even once we generalize this idea of inner product to higher dimensions. All you got to do to see if these 2 vectors are orthogonal to each other. That's the cool word we're going to use for this. It makes it, if you use that, it'll make you sound like you know what you're doing. Of course, then you got to back it up and really know what you're doing. But we would say, oh, those 2 vectors are orthogonal because their inner product is equal to 0. So a key idea that we'll exploit over and over and over and over. I know I keep saying, oh, key idea, but yeah, we're hitting the real fundamental things here, setting up this the scenario that we're going to be studying linear algebra under. And so all of these things in this set of notes are very, very key fundamental ideas. So anyway, inner product equal to 0, you got 2 orthogonal vectors. They are at right angles to each other. Let's explore this idea. Is there more to be had from an inner product about the angle than just, well, when the inner product is 0, they are at right angles or orthogonal? Let's see. So let's just set up a little experiment here. Let's take one unit vector that lies along the axis. So u is the standard vector, 1, 0. And let's take our other vector here. We used this formulation when we were talking about a unit vector, the generic unit vector in R2, but now we've given it a length a. So this vector has length a, so that's why I write that next to the vector, and its angle to the x-axis or the horizontal axis is theta. And so that's what we got there. And so let's look at this. If we were to compute the inner product between these two, and I've set this case up so that it kind of works out nicely, look what ends up happening. If I do the inner product, I'm going to do a 1 times a cosine theta. That gives me this. And then I do a 0 times a sine of theta. So notice that the 0 causes this term to go away, and I'm left with just a cosine theta. So at least in this case, the inner product does give us some information about the angle between the 2 vectors. Now, it's also got the a out in front, so it doesn't tell us completely about the angle. And there's also an uncertainty. We know that if I told you cosine of theta is equal to, say, 0.5, there's going to be 2 different angles that would give you that cosine. So it doesn't tell you exactly what angle it is, but it gives you some characterization of, kind of the angle between the two vectors. So that's how we often use this idea of an inner product, is to capture the idea of the angle between two vectors, or to measure and say, hey, are both of these vectors pointing in kind of the same direction, or at least close to the same direction, or are they, not doing that? And so it's a way of comparing, say, one entity that we might measure to another entity that we might be looking for. So think about pattern matching, or facial recognition. Suppose we had a vector that we extracted from a stored face, a stored picture of a face, and we took another picture of the same person and we extracted the same kind of vector from that. We might be able to ask, are these two vectors alike? And if they're very much alike, we would use that characterization to say same face in the photo. Now, that's how it actually works. There's a lot more going on in there. The trick is knowing how to extract a certain important set of vector characteristics from a photo of a face. But that's the underlying idea, comparing two vectors and asking, are they similar to each other? So let's generalize this idea and see how that works. So we've got two arbitrary vectors in Rn. The inner product between u and v gives me a single number that's computed by, so you got to get used to just reading the general math notation. Don't freak out at this. It's a simple rule. It's simply saying start at I equal to 1 and take u1 times v1. Now bump up I to 2 plus, that's what the big sum symbol says, plus u2 times v2 plus u3 plus v3 plus all the way out to un times vn. It's as simple as that. So given that that's how we define our inner product, and it's in terms of summations, we can use that properties of summations to show certain things. So if I have one of my vectors that ends up getting multiplied by a scalar alpha, it's easy to show with this definition. And if we were in a math class, we'd be proving these things, but I'm not going to prove it. But you can just verify this for a couple cases. I can pull the alpha out in front. And if there's a beta multiplying the second one, I can pull that out in front. Now, just a word of warning. If we're talking about complex vectors, no longer Rn, but Cn, there's a little bit of a tweak to this property. I'm not going to dwell on what it is, but there is a little tweak. So if you do ever go into complex valued vectors, read carefully before you head off into that world. Some of the results that we're talking about change just a little. If we add together two vectors and then do an inner product with some other vector u, we can just do u inner product with v and u inner product with z, and then add their individual inner product results. And it doesn't matter whether the addition happens first in the first element of the inner product or the second. Works exactly the same way. The concept of inner product links to the norm, well, at least the norm squared. So I think you can verify that when we have the same vector going into both sides of the inner product, we're going to get a u1, well, let me do it with v. We're going to get a v1 times v1, so that's v1 squared, plus v2 squared, plus v3 squared. Add them all up. Hey, there's no square root wrapped around this, so that gives us the norm squared. So once you have an inner product, you can compute the norm in terms of the inner product. Very nice result. And then there's a famous inequality, a German mathematician named Schwarz. If you want to pronounce it more like the Germans do, you would pronounce the W as a V. Schwarz, something like that. I don't pretend to be able to properly pronounce German things, but I believe that's how it's pronounced. And in German, Schwarz actually means black. So I think this is the last name in Germany that's kind of equivalent to the name Black in the United States, or in England for that matter. But anyway, important inequality. If you do an inner product between U and V and take the absolute value of that, because as we'll see, the inner product can take on negative values, that number must be less than the norm of U times the norm of V. And again, if this were a math class, we'd prove the Schwarz inequality. And then we'd be using it over and over and over to prove other things in various theorems and so forth. But we're not going to do that. And then here is how we characterize the idea of using the inner product to capture something about the angle between two vectors. So if we take the inner product between U and V and then divide by their norms, there should be no 2 here. I forgot to take that off. There's a reason that I had that there in some other notes, but in this set of notes we don't really need it. So that's just our norm. It's not norm squared, just norm. So I divide by the norm of U times the norm of V. I get just cosine of theta. And really, it doesn't matter whether that tells me that there are 2 different angles that will give the same value. If we think about cosine of theta versus theta, so here's theta, and I look at cosine of theta, so it's going to be something like this, and let me extend it this way. So there's one complete cycle of cosine of theta. So if I measure a value for cosine of theta, so I'm measuring that on this vertical axis. So suppose I get this number from my inner product. That tells me that they're either at that angle or they're at that angle. But those are negatives of each other. So really this isn't telling us, positive or negative. It's just telling us the angular separation between them. So in that sense, it's completely unique. I've got U and V. There's U, there's V. I'm just trying to measure the angular displacement between them without, saying, V is downward relative to U. That's what the sine part of that, the sine of the angle would tell me. That's SIGN, not SINE. So in a sense, this inner product normalized by the norms is telling us how closely aligned these 2 vectors are. So when the angle is close to 0, we're going to be up in this region. So a normalized inner product that's close to 1 says that those 2 vectors are very close to pointing in the same direction. They're very similar to each other. And notice that if they were pointing in opposite directions, I would be down here, 180 degrees apart. I'd either be here or here. That's going to be cosine of theta is -1. So when the inner product is equal to -1, this normalized inner product is equal to -1, then it's telling me that these 2 vectors are pointing in opposite directions. So they're alike, but kind of in a flipped alikeness. Okay, so that could be important sometimes. And what about when the cosine is equal to 0? Well, we've already seen their angle is 90 degrees. They are orthogonal to each other. So they are very unalike. One's pointing in one direction and one is pointing exactly across it. So those 2 vectors are not alike at all. And so that gives us this idea. This normalized inner product, we've just argued, lies between -1 and 1 because cosine of theta lies between -1 and 1. And it measures kind of the directional alikeness of these 2 vectors. And so, in pattern recognition, facial recognition, those kinds of things, we're looking for a face that we've measured whose vector that we extract from that face aligns with the stored vector for a stored face that we have. And don't worry about where we're getting these vectors from. We extract certain things from them, like spacing between the eyes or distance from the tip of the nose to the eye socket, things like that, facial characteristics that get extracted and then stacked into a vector. And then we do the same thing with a test image of a face, and we then compare. And if we get a number that's close to 1, we say, these are a lot alike. If we get something that's close to 0, we say these two things are very unalike. And in the facial recognition case, it's not my area. I don't think you could actually get a -1, but I could be wrong. But usually we're looking for, the +1 tells us that they are alike, and something close to 0 tells us that they are very unalike. So +1, U and V point in the same direction. 0 is when they're at a right angle or orthogonal, and -1 when U and V point in opposite directions. And obviously we can have values other than those 3, but those are the 3 touch points or milestones that we look for. So as we already said, 2 vectors are said to be orthogonal to each other when their inner product is equal to 0. And if they're orthogonal and they each have unit length, then we say that they are orthonormal. So the normal comes from the norm idea, that they've been normalized to unit length. So orthonormal vectors are things that will be cropping up over and over and over as we go through this course, and as you move into applying these ideas in EE and COE courses, orthonormal vectors play a huge role. So here's a little exercise. Suppose I have some arbitrary vector, CD, and I've been told that if I take an inner product of that with some vector R that looks like this, I get the number 1. Aha. And, well, we don't know that these are normalized, so we can't really say that that says anything about them being aligned. But we know that X inner product with S equal to 0 tells us that X has to be orthogonal to S. So what C and D values do we have here? So pause the video, see if you can work that out, or at least write down some equations that will allow you to figure that out, but maybe you can take it all the way to the end. So go ahead, pause the video, and when you unpause it, you'll come back to the other to the next slide. So here's our solution of that. If we take, these are not negative signs out in front of here, those are bullets. So if we take x dot r is equal to 1, so if we take C times 2 plus D times -1, that gives us that expression. So that's the inner product, and that has to be equal to 1. So we set that equal to 1. And then do the inner product with S. So we're going to do C times -1 plus D times +2. Add those together. That gives us this left side, and that must be equal to 0. And so we set that equal to 0. So there's 2 equations in 2 unknowns, and we could easily solve those. I encourage you to use the methods that you learned back in your maybe high school days, or first, maybe in a calculus course or a physics course or something. To solve those 2 equations, you can find out what C and D is. Then you can go back and check, draw them on an axis, and you know that X has to be orthogonal with S. So you can double check that. And then here's a challenge question. And it's actually not that challenging, but we've got 2 arbitrary unit vectors. Prove that their inner product is equal to cosine of theta. We've actually set this up so that that's pretty easy to figure out. So it's not that much of a challenge, but give it a shot anyway. And that's the end of this set of notes, and I'll see you in the next video.